Hello everyone, this is Jubayer and I'm presenting a data hiding system in static random access memory SRAM. My advisor Matthew Hicks and I wrote this paper and we are from Virginia Tech. Here's the story. James Bond wants to transfer some data out of a country. Very benign message, nobody cares about it. But border guards are very strict. They're checking every device for possible top secret information smuggling. Password is not helpful because the adversary, the border guard, they can just coerce him into unlocking the device using the classic, inexpensive, fast, password breaking machine, Raverho's attack. This is where steganography comes in. It is information hiding method that allows plausible deniability. We can just lie about the information's existence. The importance of data hiding is growing as border scrutiny is increasing in certain part of the world, and also hiding crypto wallet has become an important aspect of crypto world. There are practical examples such as a journalist trying to hide memory card in their own just to carry out some human right violation document out of a country. We designed a hardware steganography method using on-chip volatile memories. Before going into the details, let's see the formal threat model first. Alice wants to transfer some sensitive data to Bob through a covert channel, or she just wants to store the message for herself but does not want anybody to know about it. The adversary can inspect a device, copy its content, erase it entirely, and override it. Even can run mathematical analysis on the memory dump of the system. We call our method invisible bits. It's an SRAM-based steganography technique that hides information in the SRAM's power-on state. SRAMs are the building block of all kinds of on-chip memories, including cache and registers. Here is a picture of Mona Lisa that we are encoding inside of this random-looking pattern. This is a bunch of SRAM cells value when they boot up, meaning when the system still did not write anything to the caches, for example. Once done encoding, the power-on state becomes an information carrier that kind of molds itself into the shape of the message. First, let's understand the fundamentals behind invisible bits. This is an SRAM cell. If we strip down the cell to basic, this is the loop that stores information through a positive feedback between cross-couple inverters A and B. When we switch on a device and take a snapshot of the entire SRAM array, for example, we see this 50-50 spatial distribution of ones and zeros scattered all over the array. This is the power-on state of an SRAM array. If we take a snapshot of cache or most registers, we'd see this kind of a random ones and zeros spatially distributed in the array. A little bit more on the power-on state. Inverters in the cell are symmetric and balanced by design, meaning they are same electrically. A and B, they have similar electrical characteristics. So when we boot up, it has 50-50 chance of being 1 or 0. This is due to the hardware race condition that takes place when we switch on an SRAM cell. One inverter is trying to turn on faster than the other. So if inverter B wins the hardware race condition, it will power on as 0, and if A wins, it's going to be 1. Our idea is to direct this balance so that the cell power on into a value that we want. We exploit aging to do that. So here's a little physics. When a transistor is in operation, it experiences numerous physical phenomena such as bias temperature instability and hot carrier injection in the gate oxide, which increases the voltage because there are charge trapping in the gate oxide. And the ultimate effect of such charge trapping is the slowing down of the transistors over time. And here is what happens for an SRAM cell. Let's consider a cell powers on into a logic 1. Because you can see from the gray curve, A is winning the hardware race condition, and so the cell is booting up into logic 1. Now if we keep the cell for years in this state, inverter A is going to slow down because M4 is a PMOS and it is under stress due to negative bias temperature instability known as NBTI, which means B will win the race condition from now on once the aging took place. So aging the cell with 1 just flip the power on state from 1 to 0. This means data in the cell directs the future power and state. Therefore, we can encode information in the hardware race condition using data and aging. Aging-induced change takes decades to impact the circuit performance. We cannot wait for years to encode information clearly, but we can accelerate the process. Transistor aging accelerates when electric field density in the gate region is high, so let's increase the voltage. And also thermal stress increase aging speed, so let's fire it up, basically bake the device in higher temperature. To understand the acceleration process that happens in aging, we write all ones to the SRAM of an MSP432 microcontroller and bake it in 85 degrees Celsius at an elevated voltage 3.3 volt. The nominal for this device is 1.2 volt. We'll see number of ones are reducing and a lot of cells are flipping their states from 1 to 0, over time reducing the number of ones. This is the optimum condition for aging. Increase the temperature and increase the voltage. Now let's move on to the actual encoding system, how we encode information in a large SRAM array. I'll explain the encoding process and the system using single bit information burn-in. The method remains same regardless of the size of the SRAM and the message that we want to hide. So let's encode value 1, logic 1 to this cell. First we write logic 1 to this cell and then we increase the voltage and the temperature and then we wait for it to burn in. Encoding parameters, total stress time, voltage and temperature depend on the device that we are using to encode information. So we need to seek guidance from the datasheet to decide these parameters. At the end of the encoding process, the data will burn in the power on state of the cell. Therefore, it will power on into logic 0 from now on, because we deliberately slowed down the inverter A by aging. As far as data encoding is concerned, we have hidden logic 1 in the cell because it will always power on into logic 0 from now on. That is, the data leaves an inverted burn-in effect of itself, kind of a negative image. Information decoding process involves just dumping the power on states and complementing it to interpret the message. To dump the SRAM, we need to introduce a software before a system overrides the power on state of the SRAMs. For example, loading operating system will override the cache contents, which we must prevent by dumping and storing the cache contents before the OS is loaded. The evaluation of our system answers two questions. Since this is a physical process, can we retrieve the entire information once we hide the information in SRAM's analog domain? Is there anything that tips off an adversary? Is it really plausibly deniable? We evaluated invisible bits in 12 devices that includes single-cycle microcontrollers to quad-core application processors from ARM. Here are some example retrieval accuracies that ranges from 79% to 97% without any error correction. The information encoding time varies depending on the device that we are using. Retrieve message will have some error if there is no error correction method implemented with the encoding mechanism. The main reason is when we cannot change the power on state into a desired logic value, no matter how long or how hard we try, this will introduce error. As I said before, inverters in a cell are symmetric by design, but when we manufacture them in real silicon, due to manufacturing variation, the inverter A and B can be so biased, so different, that regardless of extreme aging for many hours, some cell will not change its power on value. Clearly, this is going to introduce error. Aging-induced change partially recovers naturally. When we just keep the device without power, oh, this is a problem for James Bond. Well, this is because physical change will revert and try to go back to the original state if we allow some time. Therefore, some of the cells will go back to the original power on state after some time, reducing the message's retrieval accuracy. Fortunately, aging-induced changes are logarithmic with time, that is, the rate of the change reduces as time goes on. As you can see, a few days later, the recovery rate reduces significantly, and we can maintain a 10% error level even after a month. How can we improve the error performance? One way is to stress the device for longer and then age it more, but aging-induced changes are logarithmic and it will virtually stop responding after a certain period, maybe a couple of hours. The other option is to use error correction. The error in encoding is largely random as we analyzed it, and considering each bit a Burnley trial, we use multiple copies of the single bit as a means to correct the error. This is the simplest form of error correction. So what is happening here is we are encoding one bit of information in multiple bits, basically copying the same message many times and applying the majority voting on them. So as you can see from these images, as we increase the number of copies, the message extraction accuracy improves and the image gets cleaner and cleaner. Since this is a very low code rate error correction method, by layering another higher code rate correction such as Hamming 7.4 would definitely improve the performance, as you can see from the black dotted line. Now the second most important question, how is it plausibly deniable? How are we being able to lie that we don't have information and an adversary will believe us? So first, we're not really storing information in a permanent storage device. And second, we're not restricting system from using the SRAM. The system is free to use any part of the SRAM, no matter if it is encoded or not. So how is someone hiding information in there? As soon as the system loads the operating system or starts using the SRAM, SRAM will lose the power and state. It will be initialized and the message will be inaccessible from typical software stack. This is already providing plausible deniability. But what if an adversary decides to look at the power on state and by manipulating the firmware itself? This will reveal the hidden payload. Because once the message is encoded, power on state will not keep its typical properties. Let's look at this table. A clean device's spatial autocorrelation and mean power on state bias deviates from its typical values once we encode a message in plain text. Same thing happens to the entropy of each byte. It reveals the hidden message. To strengthen the plausible deniability, we encrypt the information, and that would destroy the message's spatial structure as it becomes 50% 1 and 50% zeros uniformly. Ultimately, encryption will bring the statistical properties of an encoded device at the level of a clean device. This would maintain plausible deniability even for a stricter adversary. Now that we have established everything that we need to make information invisible in SRAM's power on state, here's the final system. First, we add error correction code with the message, and then we apply an error-neutral method of encryption such as AES in counter mode. Well, any stream cipher will work really. And then we load the encrypted message in the SRAM and expose the device to an accelerated aging, increasing the voltage and temperature and then allowing it to physically burn in the data inside of the transistor's analog domain. On the receiving end, we need to follow the same steps in reverse. Before interpreting the message, it must be complemented, and then we apply the encryption algorithm on top of it. The assumption in this system is that the key is pre-shared. State-of-the-art for the hardware-based steganography method are the flash-based methods. And these are the closest related work that we compare invisible bits performance to. The first one is flash cells program time-based method. This is from an Oakland 2015 paper, and the paper encodes information in the time it takes to program a flash cell. Longer program time encodes logic 1 and shorter program time indicates logic 0. To manipulate the aging time of flash cells, authors use device wear out, that is aging. This method needs a few hundred cells to store 1-bit information, so information capacity is rather low. And also, we need to provide sufficient interval between flash pages to avoid interference in the hidden data. The second method is a voltage-based method, similarly for flash cell. It improves the program time-based method's capacity by twice x using voltage to hide information instead of program time. In this method, the authors encoded hidden data in between different programming voltage levels of a flash cell, basically slowly and controllably programming a cell such that it carries additional hidden value other than the value written to it by a typical software. So basically converting a single level cell to a multi-level cell. This method cannot withstand eraser and overwrite. So if an adversary copies the data, resets the device to factory, and reload the data, although the normal user level data will be there, but the hidden data will be gone. Invisible bits solves all this limitation. It carries high density information in any device, including small microcontroller to fully application level processor that has no flash memory. The message is encoded through aging and virtually indestructible without risking a device's permanent damage. It could break a device. Okay, so I said a lot of things so far, but here's the summary of what I said. Invisible bits, our method, hides information in the SRAM's analog domain by encoding the value through circuit aging. And SRAM is not really volatile, and we can save data there permanently, and we can just lie about the position of the data. And this is our system, Invisible Bits. For questions and comments, please reach out to the following email address.